NoSQL document stores are increasingly deployed in today's data-intensive organizations. The technology is constantly evolving. This introductory slide deck covers foundational concepts, while later decks will address implementation and implications. The idea here is to talk about how the use of a NoSQL document store system such as MongoDB can deliver low-cost performance ratios, fast response times, scalability, and schema flexibility. Perhaps the main theme is increased parallelism. By the time you review these notes, many things will have changed. For example, many valuable NoSQL features have been added to the well-known database management systems that were once strictly relational. And many of the powerful management features built into traditional database managers are being added to NoSQL platforms. Still, the lessons learned here will be instructive even as systems and platforms evolve. Let's begin by contrasting relational data with the kind of documents used in a document store. Relational data has been organized into tables with rows and columns. Each table is a list of a particular kind of thing. As in the design on the left, we might have a table that lists tests, another table listing students, and a third documenting which student took each test. Each column stores a particular attribute. A table of tests might have attributes such as course, title, and date, and each row in a table is a record of one particular item of the list's type. So a table of students might have a row for Wei, another for LeBron, and a third for Nathan. In contrast, hierarchical data, the kind usually stored in a document store database, organizes things so as to keep closely related items together. As in a relational database, the documents stored in a record for a particular test might include attributes such as the name of the test and the name of the course. But in addition, it might store a list of everyone who took the test and each of the questions on the test. Instead of breaking up data based on the kind of thing it is, related data about different kinds of things is mixed together in a single document. Running process tasks in parallel means that several steps are happening at the same time. In the first animation, tasks 1, 2, and 3 will each take the same amount of time in both the single and parallel process groups. Watch how this works in the animation. Because the parallel process tasks run together, they finished well before the single process group. This idea of doing operations in parallel is a key driver of increased NoSQL performance. Think of the processing lanes above as computers. The single process example uses 1, the parallel example uses 3. So parallel has to be faster, right? Well, maybe. Let's rerun the simulation with tasks moving along 4 times faster in the single process. This time the single process finishes sooner. This is not the time for a discussion of queuing theory, but in choosing a database management architecture, total performance can depend on a number of factors. All things being equal, a parallel system will complete its work far sooner than a sequential process where each task has to wait for the completion of previous tasks. Making multiple components work together requires coordination. The narrative on the slide describes a process for fixing a broken table that comes into a busy repair shop. Sally assigns someone to work on it. Ahmed assigns subtasks to Sydney, Kaylee, and Johnny. Ahmed fixes it and gives it back to Sally for distribution. Besides the step where Ahmed actually fixes it, the rest of the tasks are all coordination tasks. Today's multi-tiered, data-driven systems require a lot of coordination. Tasks are assigned to one of several computers in a grid. Data is gathered from various sources, which may be connected through a network. Resources are locked and released, and outputs are delivered to external participants. Optimizing interactive processes is complicated. For example, in our example, Sally could just fix it herself. But if there are lots of repairs coming in, she might get overloaded while Ahmed is available. Every worker could have their own hammer instead of having Johnny fetch one. but buying hammers might be expensive. The time needed to acquire resources such as glue and nails depends on where they are and how hard they are to find on the shelf. In short, processes require coordination, and optimizing performance and cost involves making trade-offs. In addition to coordination costs, systems face control costs. Controls are intended to mitigate risks. Consider these risks and controls for our repair shop. Repairs might be delayed because supplies are unavailable, so we keep track of the supplies on hand. Someone might send us work to do that we are not supposed to do, so we check the warranty for items we are asked to fix. We sometimes use tools that can really hurt people, so we carefully monitor who checks them out to reduce both suffering and liability. Poor repairs would make our customers mad, so we check each repair to verify it was done right before we send it out. We need to get paid for our work and continuously improve our processes, so we need to carefully track activity. These risks and controls from the repair shop are somewhat like risks faced in managing data-driven systems. The same data may be used by multiple processes. We need to coordinate sharing. We need to validate who is using our system to control costs, ensure revenue, and manage workloads. We don't want everyone to access all our data because some of it is sensitive, valuable, or regulated. Complex processing can fail for many reasons, some of which are beyond our control, so we want to notice and address failures promptly. Although it is easier to perform a task and move on, system logging can be vital for performance tuning and process improvement. These are some key control issues facing today's systems. Protecting systems is important, but it usually slows things down. It is important to choose wisely when deciding which controls you want to pay for. So far, we covered 4 concepts you need to understand to move on with the discussion of NoSQL document store benefits. First, relational versus hierarchical data. In a relational database, data is separated into different lists for different kinds of things, whereas in a document store, different kinds of things that are closely related are stored together. In the relation example, 3 lists would separate student names from test titles. In the document store example, 1 document would contain both the test attributes and the related student names. Second, parallelization. All things being equal, performing several tasks at once will get the job done sooner. Third, coordination costs are incurred in scheduling or managing processes. It's not just about doing the work, it takes time and effort to coordinate the activities of multiple actors. Finally, control costs to mitigate risks are embedded into processes to ensure success. Controls help us ensure success, but they may be costly or introduce delay. Computers keep getting faster, but faster is expensive. And even the fastest of computers cannot single-handedly manage the load of today's massive data management tasks. Large-scale web applications have to remember things about hundreds of thousands of simultaneous users, and dealing with data requires data transfer and data sharing. A high-powered web server may be able to do the computations needed to support 1 million users, but those computations are often delayed as they wait for data to arrive through a network. To address this problem, system designers divide the processing load across many computers. For example, a large-scale web-based retail site would employ multiple web servers to share the load. When a user logs on, their app talks to any one of the web servers. Some coordination is still needed. For example, some load balancing equipment has to decide which user talks to which server. If the cost, in time delay, associated with routing each user to a particular web server can be kept low, and it can be kept low, many servers can work side by side in parallel. Each server is talking to a subset of the currently active users. So why are we talking about this in a database class? Well, because systems usually need to share data, and it's not so easy to share data across dozens of independently operating systems. Modern multi-tier systems separate processing from data management. In the picture, data needs for many users all eventually make their way down to a single choke point, the database server. Many of the advantages of a NoSQL system are achieved by either providing parallel handling of requests with lower hardware and software costs, or by reducing the coordination costs associated with responding to multiple requests. It is important to note that this is an oversimplification. Actually, powerful relational database management systems can be configured so that they employ multiple servers and many process requests at the same time. But NoSQL systems were designed from the start to support parallel processing. Most relational database management systems run on a single, very fast computer. In contrast, document store systems such as MongoDB split up the tasks done by the database server and run them on multiple computers. Document store architecture decomposes the tasks. Master nodes accept and manage requests, transferring stored data back and forth with data nodes. This image shows a prototypical document store database installation. The single database server has been replaced by several master nodes able to accept requests for data. These master nodes then direct their specific data requests to one of several data nodes. It is very important that to realize that this is an oversimplification. There are still coordination costs in a NoSQL environment. Routing requests to available master nodes or to data nodes containing the right data still require some level of communication between the servers. Still, the basic idea is instructive. Many organizations are achieving high performance at reduced costs using this architecture. The next slide deck in this series covers sub-strategies that support time and cost-effective parallelized document store infrastructures.